let's go to window and this and that. So you can see now, right?
Yeah. Yeah.
Okay.
Just a moment. Yeah. Now it's perfectly. Yeah. It's there.
So I would
So
like
let's
to.
start.
Okay, so I would like to thank Ravi for this invitation. Actually, Ravi and me, we did our masters at the same place at IISc Bangalore in India, and Ravi was a year junior, right? Ravi, you were a year junior to
Yeah.
me,
Yeah.
right?
Exactly.
So, so it's great that Ravi got in touch with me, and then he said, "Would you like to present?" And I said, "Why not? That would be perfect." So, you know, so we ended up giving this talk. So,
Yeah.
okay. So in any case, if you, because I cannot see people when I'm presenting for some reason, I don't know what's actually the thing. So to be honest, I don't know how this happens, how I can have people with the talk and the people along with here. So what I'm going to do is that I'm going to go through these slides a little slowly. I mean, a little slower than I anticipated. And in case if you have any issues, any problems or anything that you don't understand, just stop me and ask. So this talk is titled A New Approach to Classical Pólya Urns, and it's infinite color generalization. And it is a joint work. So it's based on two joint works, one with Antar Bandyopadhyay from ISI Delhi, and another one with both Antar Bandyopadhyay and Svante Jansson. So Svante is from Uppsala, Sweden. So let's start. So does the page down not work on this one? Just frozen.
Uh, it, it will be working on your computer.
Yeah, but it's sorry. Right.
Yep.
So this is
Yeah.
the basic outline of the talk. And the basic outline of the talk, the bullet one tells us that in this we are going to motivate why we are at all studying infinite color and models. What's the motivation? And we are going to introduce the model. Well, not introduce, we are going to define the model. The introduction is not really entirely due to only us. And then we are, this representation theorem part is the most important part of this talk, where we are going to discuss this thing, a kind of coupling of the infinite color on model on a structure called the random recursive tree, which is represented by, which is abbreviated as RRT, and another process on this random recursive tree, which is known as the branching Markov chain. So I'll come to all these definitions later on. And then we are going to see some main results, which are actually applications of these coupling, and discuss some future projects. So let's first try to motivate our talk. Let's first try to motivate our model. At all, why should we study it, whether this is of any use or not? So, okay. So, right. So let's first start by defining the finite color urn model. The finite color urn model is a very simple process, and I'm sure many of you know it already. It consists of the following. It's in the simplest way. I mean, in the simplest classical model, it was first introduced by Pólya in 1930, and that is a seminal work of Pólya now. And what is the model? Well, let's say that we have a big urn or a big basket in which there are two different colors of, there are some balls and they are colored differently. Some of them are colored, I wrote white, okay? So some of them are colored white and some of them are colored blue. And we are given some u0, so some initial number of white balls denoted by w subscript 0 and blue balls denoted by b subscript 0, a replacement matrix, a matrix R, which is termed as a replacement matrix. So this is an initial data, and we are putting some condition on R, which is that R has non-negative entries, right? So for the purpose of this talk, we will actually take R to have non-negative entries, but that is not important. So what are we going to do? So we are going to do the following. At any given time, for example, at time 1, we are going to put our hand in this basket and we are going to draw a ball uniformly at random. We are going to note its color and we are going to put it back. Now, say the color of the ball is white. This matrix R is indexed by the set of colors which is white and blue. So in this particular case, this is a square matrix of order 2 cross 2. So we are going to look at the row corresponding to the white ball because we have noted that in the first trial a white ball has been selected. That row has some entries. So those entries are the number of balls that we are going to add. For example, say WW, the entry corresponding to WW, the indexing WW is actually the number of white balls that we are going to add, and the number corresponding to WB is that when we are choosing a white ball, the number of blue balls. So this is how the process is going to evolve. In the next trial, we are going to choose from whatever U1 is. So if we write that down formally, that means that at time n plus 1, a color Zn. So this is now the random color. Note that I am not saying we are choosing a ball, but we are choosing a color, and there is a reason why I am saying that we are choosing a color, and I'll come to that in a couple of slides. So we are choosing a color uniformly at random from the current configuration UN. So basically this equation tells us that our selection procedure is uniform because we are choosing Zn proportional to Un. That's exactly uniform. So if we had, say, Un to the power alpha, then it was superlinear, something like that. In this case, alpha is 1, so that is uniform. And we are updating the current configuration Un to Un plus 1 by adding the row of R that corresponds to Zn. Right, because in case Zn is white, the color chosen is white, we are going to update by the row corresponding to the white color and so on. So that gives us the complete evolution of the process. Now observe the following, that this because okay, let's go one step at a time. This quantity Un is a random measure. Right? It's a random finite measure. So it's an L1 measure. And if Tn is the total number of balls present in the urn at any time, so that means Tn is the sum of the white and the blue balls, then Un by Tn is actually a random probability measure. Why is this a probability measure? Well, why is this a probability measure? Because we have assumed the following, that R has no non-negative entries. R has no negative entries. R has only non-negative entries. Therefore, we are only adding, Un has only non-negative entries. Therefore, Un by Tn is actually a random probability measure. So now if we put some conditions on this matrix R so that we know the asymptotic properties of this quantity Tn, then studying Un is same as studying Un by n plus 1, as long as we know the asymptotic properties of Tn, right? So this gives us an alternate way. So this gives us a hint as to how should we study these processes. What's an alternate way of studying these processes? So just I want to stop here. Is a can I mean is the connection and everything okay?
Yeah, everything is cool.
Okay, okay, just to make sure because I can't
Yeah,
see people. So
yeah, no
so
problem.
this gives
I will be
okay,
I
thanks.
will be taking care of it. Don't worry.
Okay, okay, Ravi, thanks. So this is basically this gives us an alternate way of studying the process. Instead of thinking of un, as as a vector that gives us the number of balls, we can think of un, well, by Tn. So un is also a measure, so we can think of the entire urn model as a measure valued process. So let's make that assumption, one such assumption on R, so that we can actually study Tn and therefore study Un by Tn, right? One such assumption, of course, we have already made this assumption that R has non-negative entries. Let's assume that all the entries of R are not necessarily integers. Now, this can be a bit counterintuitive because we may think that okay, we are selecting a ball, but instead of that think that we are selecting a color. So you can think that the urn itself is like when we go and want to paint our houses, we go and say, we ask the people that okay, we show us some colors, and they show us some colors, and then they start mixing them. So you can think of the urn as a huge blob of different colors, and then these individual entries of un, of the vector un, you can think of the weight of the different types of colors there. So instead of thinking of instead of imagining this entire thing as the number of balls, you can think of them as the proportion, or the weight corresponding, not maybe proportion. Proportion is a bad example. You can think of them as the weight corresponding to the different colors. And once you think like that, you can easily assume that these entries of R are not necessarily integers. So so this is just a definition. If we assume that all row sums of R are, say, C, some quantity C, which is of course non-negative in this case, then R is said to be balanced. So once R is balanced, let's go back a couple of slides, then this quantity Tn is something like the L1 norm of U0 plus n times C. So therefore, we know how Tn behaves. This is just one of the assumptions. We know how the asymptotic of Tn behaves. And in that particular case, this becomes something asymptotically, something like un by some n. And then we studying un is same as studying un by some n. Why we are taking un by n will be clear in a bit. So how does that help will be clear in a bit. So if R is balanced, so when R is balanced, well, I already said that R is referred to as the replacement matrix or scheme. And when R is balanced, if you normalize R by its balancing sum, by its row sum, then R is actually a stochastic matrix. So when R is balanced, you can think of the entire thing as a stochastic kernel. So this is a very important step, the associated Markov chain. So what we are saying is that when we are given an urn model, if we are, so now from henceforth we are always in the balance scenario, and if we are in the balance scenario, then we can say that okay, I'm going to normalize by the balance, and therefore I have my replacement matrix R to be a stochastic matrix. So once we do that, then we can say that okay, once we are given an urn model, so the initial data is some U0, a stochastic matrix, and the stochastic matrix R. Once we are given that, we can construct another Markov chain, which we call the associated Markov chain and denote by xn, which takes values in the set of colors S. So in particular, you can always think of S to have two entries in this case, say white and blue. So the initial distribution for this Markov chain is U0 by T0, and the transition probability matrix or the Markov kernel in this case is R. Why I am doing this, I will be clear in the next slide. What's the advantage of introducing an extra thing like this associated Markov chain? So basically that's the definition, whatever I have told you. So if R is a balanced matrix, then we can construct an associated Markov chain on the set of colors, and vice versa. Given a Markov chain, we can always construct a balanced urn model. But what's the purpose of creating this extra burden of a Markov chain? And the answer is the following. Sorry, well, the answer is not exactly this following, but this suggests a way of defining the entire thing on infinite color. We can come to that later, but what's the purpose of this associated Markov chain is the following, that the classical literature on the finite color models have always suggested that these urn models are the asymptotics of these urn models are guided by the qualitative properties. And by qualitative properties, I mean, say, for example, the transience or recurrence or positive recurrence or whatever you want of the, well, we are in a finite case, so let's not say everything is positive recurrence. So let's say just recurrence. So associated property, sorry, the asymptotic properties of the urn model, that means UN by N is guided by or is completely determined by the qualitative properties of the associated Markov chain. And say, for example, the associated Markov chain has a stationary distribution. Then it's a very popular result due to various authors, one of them being Raoul Gut, and then Atreya and Ney, Svante Janssen, Bayan, who there are many people who proved this second bullet, that the limiting configuration of the urn model or the profile of the urn model converges to the stationary distribution of the associated Markov chain. So the question now remains that what is the actual relation? The actual relation or the actual embedding or the actual coupling was never explicitly stated in literature. So you see, once we find this actual coupling, life might be quite easier for us in terms of the urn models or from the perspective of the finite color classical urn models. So that was one reason why we introduced the infinite color version, because Markov chains on infinite state space has much richer asymptotic properties, has much richer properties, right? So we decided that we would study the entire thing in the infinite version, and then that would give us much richer properties. So that's one motivation to study, maybe a theoretical one or maybe two mathematical, but that's a motivation to analyze the infinite color version. And as I said, the infinite color version can now be defined or explained verbatim. So let's just do it in a flash. You can just verbatim copy paste what we had for the finite two color case. So let's say we are in a Polish space. The set of colors S is some Polish space. We put some nice sigma algebra on it. We define the finite measures, which we denote by this calligraphic N, and this calligraphic P is the set of all probability measures. And we have seen that under the assumption that R is a stochastic matrix, this entire urn models can be thought to be measure valued processes. So let's just do that. So let's take R to be a Markov kernel. Let's take so our process evolves exactly as before. So if UN is the given configuration of the urn, which is now a finite measure at any time n, then Zn is a randomly chosen color. which the conditional distribution of which given the past is, so basically it's a uniformly randomly chosen color. So that means the probability that Zn is in some set A is proportional to Un of A. And then we do the usual updating. So Un plus 1a is Un of A plus R of Zn of A. So this is the kernel. Just one more assumption. We take U0 to be a probability measure. Well, we can also take U0 to be a general finite measure. We of course need U0 to be a finite measure because we need U0 to be basically a small L1 vector. Otherwise, uniform selection for the first time for Z1 won't make any sense, right? So we need U0 to be a finite measure. And a finite measure can be, there is a slight loss of generality which can be tackled. So if we take it to be a probability measure, but so just think that a finite measure, you can always normalize it to get a probability measure. So let's stick to this for the time being. So in this case, since R is a stochastic kernel, so the normalization of Un is by n plus 1. So we are going to study this quantity Un by n plus 1, which is the configuration of the urn, and which is equivalent to studying this Zn, right? So I don't know. I don't know. So yeah, so this will be referred to as an urn model with set of colors S, initial configuration U0 and the replacement kernel R. So of course, again, the same things happen. Un by n plus 1 is a random measure. Is a random configuration. Un by n plus 1 is the, I've already said this, Un by n plus 1 is the conditional law of Zn. And if we take an expectation here, then we get the law for Zn, which we will call the expected configuration. So that's basically those two bullets are the same. So basically what we are saying that studying Un is same as studying Un by n plus 1 is same as studying Zn. So let's first see, do we lose something by defining the infinite color urn model in this fashion? The answer is no. The answer is that for the finite color model also, basically we have verbatim copied the finite color model. So we are covering all possible cases, even the classical Pólya urn case. Then, as I said, that if we assume U0 to be a probability measure, there's a slight lack of generality, but that can be easily dealt with, and that was discussed in a paper by Janssen in 2018. So, as I said, we did not introduce this model. This model was already available in literature, and this is a paper. This was available in the classical sense, that is when the replacement kernel is identity, in the sense that if you choose a red ball, you just add another red ball, right? We have not made any such assumptions so far. We have said that R is a Markov, R is a stochastic matrix, that's all. So this paper appeared in the Annals of Statistics in 1973 and was suggested as an alternative method to construct the Dirichlet-Prior process. And they studied this only for the classical case, so when R is the identity. So now that we have discussed this model, so now we have motivated and what do you say? We have introduced or we have explained what the model is. Let's study something which would seem to be different from what we are studying, but we are going to connect them in a few slides from now. So let's see what is a random recursive tree. In this particular case, this is actually a rooted uniform random recursive tree. So we are given a root, and that's denoted by this round thing. Now a vertex comes, V0, and it has the root to attach itself to. So V0 comes and attaches itself to the root. The next vertex V1, when it comes, it will attach itself either to the root or to the vertex V0, right? How it is going to attach itself? Well, it is going to select one of these available vertices uniformly at random. So in this particular realization, my V0 has decided to attach itself to V1. V1 has decided itself to attach itself to V0. And let's say we have V2, which comes and chooses one of these available three vertices uniformly at random. So that's V2. In our case, V2 has decided to attach itself to the root, and so on. So the tree is evolving like that, right? So this is one particular realization of this random, what we call the random recursive tree. So how is it evolving? Well, we are given a sequence of uniform random independent, what's very important, independent uniform random variables, DNs, which are, so DN is a discrete uniform random variable on n plus 2 vertices. So in this case, I have said that the root is labeled as -1 because it's not nice to write root and V0 and V1. That's why I'm saying. So -1, 0, 1, and so on. So these are the vertices. And Dn will, so the new vertex, the nth vertex or n plus 1th vertex, I'm just a bit confused, but whatever. Whenever it comes, it chooses one of these vertices. So it chooses from 1 by n plus 2. So with probability 1 by n plus 2, one of these, its parents, right? So that's exactly how the tree evolves. So this what do you call this? The mathcal T is actually an infinite tree which has been constructed inductively by considering this dn. So dn basically gives you the vertex that comes in at time n. So dn gives you the distribution of the ancestor of the vertex that comes at time n, right? So this n arrow towards the left, well, we denote it like this. I don't think it's the best notation, but anyways, so and is the ancestor or the parent of the vertex n. So now we have a tree structure. So now we are going to see how there is a process on this tree structure that will be exactly our process on the random recursive, our process on our urn model that will correspond to the urn model. So this is basically the construction of the random recursive tree. So tau n is the tree at time n, and the union over all such trees will give us the infinite tree. This is just for, sake of completion. This is just for the sake of completion. So let's see this. And for that, I want to write a bit, but I cannot do it while I have the full view. So I'm going to reduce the view a bit and then going to write. Okay. So first of all, recall that Zn is the law of, the conditional law of Zn is given by un by n plus 1. So recall the fundamental recursion equation that we had, un plus, I don't know what is happening. Okay, so let me try again. N plus 1, I don't know, this is not very good. Okay. N plus 1. Okay, let's say this is plus. Yeah. 1 is equal to un plus r of zn, right? R of zn. So if we expand this r of zn into into a long hand, what you are going to get is exactly what we have, u0 plus sum over all these r zj's. I don't know, this is, my screen is not so good. So can you all see the writing?
Yeah, yeah, yeah.
Okay, yeah. So this is the longhand. Let's forget the 1 by n plus 1 and let me go back to our full screen mode again. Okay, so it stays on. That's great. So we had this, the first equation we have here was our fundamental updating equation. What we decided is that let's write it in a longhand. And now let us divide by n plus 1 both sides. So whatever we have here. See, this n plus 1 is actually corresponding to our uniform selection, right? If you think of the tree, a vertex is selected uniformly. The parent of an incoming vertex is selected uniformly at random. So it is n plus 1, or, when the nth vertex is coming, then it is n plus 2. So this is exactly where the n plus 1 is coming. And then there is a jump happening along each edge of the tree. So this tells us that we can define a process on the tree. So let's try to define a process on the tree. First of all, there is a root. The root now has been given a state. So think of that the root is in a state. There is a particle at the root which is at the state delta, which we don't know. So this is an artificial state that we are introducing in the process. And then in our tree, V0 was attaching itself to the root. So once you attach V0, you put a particle at V0. But what is the state of the particle at V0? The particle at V0 has some state W0 given by this distribution. So U0 will be at some state, say red, for example, proportional to U0R. So whatever red, so this is a vector and it has a component U0R. It will jump according to this. So we are putting edge weights. We are putting weights on edges. What is the principle? The principle is the following. If our incoming vertex is choosing the root as its ancestor, then the edge weight is according to U0. And at all other places, if the incoming vertex is choosing an ancestor that is not the root, then the jump is according to the Markov kernel. So let's see. W1 has attached itself, so V1 had attached itself to V0. So we are going to put a particle at V1 and its state will be given by this R. So we are putting an edge, weight R on this edge joining W0 and W1. And this process continues. So this was our realization of the tree. So this is how the process is going to look like. So basically we are going to call this process the branching Markov chain, and it is on a random recursive tree. Many of you already know probably that the branching Markov chain is a very interesting thing to study. So a lot has been studied about branching Markov chain on random recursive trees. Sorry, not random recursive trees, on Galton-Watson trees. And because there's a link to the KPZ universality classes, so we are just saying that we are doing the branching Markov chain, but on a different tree structure. It's the random recursive tree. So let's now formally define the branching Markov chain. So the branching Markov chain is a stochastic process Wn on the state space S hat, which is S, which is the set of colors, union with this extra additional state delta. We don't know what it is, but there is some state, such that the root is always at this state delta, and everybody else is, so if at time n the incoming vertex chooses the root as its parent, then it is at some state A with probability proportional to U0 of A. Otherwise, if it chooses some other vertex as its ancestor, then it jumps according to R, right? So that's the process. And basically, what this says is that Wn, so basically we constructed Wn from this law. So that means this Wn process, which we call the branching Markov chain on the random recursive tree, has the same law as Zn. So that is the exact embedding. Okay, so Zn as a whole process has the same law as this branching Markov chain, and that is the exact relation. See, the branching Markov chain, let's go back. So the branching Markov chain is guided by the Markov kernel R. Therefore, the associated Markov chain is related to the urn model via the branching Markov chain. So that's exactly what our result is. So how is another? So this is as a whole process, because observe that these quantities Zns, when you are looking at, they are history dependent processes, right? So if you want to say that, okay, at time 10 I have chosen a red color, what is the probability at time 10,000 I will choose another red color? The point is that this whole sequence, say Z10 and Z10,000, when you want to calculate the covariance between them, you'll have to go all the way to the past. That's the biggest hurdle of this process. What we are saying, and I will explain this more in details in one of the later slides, that what we are saying is that this branching Markov chain, because it's a process on the tree, the computation of the covariance would be much better. So we would know what is the dependence, how far, how deep into the history that you have to go to calculate the covariance or find the dependence between, say, Wn and some Wm. So that is as a process. So this is the general connection. And another thing is that when you take the marginal distribution of Zn, so we are taking the marginal distribution of Zn in this theorem too, and recall that Xn was our as usual associated Markov chain. What we are saying is that Zn has the same law as X sub tau n, where I will explain in a bit what tau n is. So basically, okay, so now maybe we are a bit happy because we see Xn explicitly, but so what we are saying is that the marginal law of the color chosen has the same law as X tau n, where tau n is kind of the depth of this random recursive tree. So what we are saying is that the urn model, due to its history dependence, is not evolving quite as fast as the Xn or the Markov chain itself or the associated Markov chain itself, but there is a delay of tau n, which is the height of the random recursive tree. And there are very nice properties of this tau n. The tau n scales like log n, and it has a central limit theorem of law with a centering of log n and a scaling of square root log n. So now that we have this exact connection, so we started with an urn model, we connected it to something called the associated Markov chain, and then we connected the associated Markov chain to a process on trees. And this is how these models are related. So we know that this associated Markov chain, we are still a bit, we are not exactly there. The couplings are there, the exact relations are there, but this is not giving you the full answer or giving us the full answer as to how this associated Markov chain is guiding the entire process. So now we have to see some applications of this or some applications of these two representation theorems. But before we go there, we must note down a couple of points, and that point is the following. So let's go back here. This sequence Dn is independent, are independent discrete uniform random variable, and they are independent of the urn process itself, right? So the tree structure on which we are defining the entire process is independent of the urn model, and that's a very big bonus for for us in this construction. So that, and that is due to the existence of this factor 1 by n plus 1. If we did not have this 1 by n plus 1, or as a matter of fact, if the matrix R itself was somehow not, okay, I'll tell you what it means. If the matrix R itself was not balanced, we would not get this 1 by n plus 1, and the tree structure would not be independent of this process Wn. And that's one big problem, when we will try to generalize it. So that's one observation. So before I go any further, these couplings were introduced by Bandyopadhyay and me, and then were independently introduced by Myler and Markov, and also they were improved by Svante, where he removed the finite measure, where he considered a weighted version for the finite measure, and that means he removed the probability measure assumption. So let's see why this is a good coupling. I mean, so far we know that there is a coupling. Whether it's of any use or not, we don't know yet. So what does it mean to be of any use? That means that the associated, so we still want to know how the associated Markov chain is guiding the entire process. We know that there is a coupling, but we don't know how that is helping. So let's see how that is helping. So what does that mean? That means that if the associated Markov chain would have some nice properties, say for example, the associated Markov chain is a random walk and it has a central limit theorem, then we expect that the urn model has a central limit theorem. Or if there is a stable law for the associated Markov chain, then the urn model, that means un by n plus 1, these random measures would have some stable law. So for that, let's make this assumption. Basically, this is an ergodicity assumption. What we are saying is that there exists some probability measure, non-random probability measure lambda, such that, and some centering of A and scaling of B, such that the associated Markov chain Xn with the centering of An and scaling of Bn converges weakly to this lambda, right? For example, you can think that Xn is a random walk. In that case, this is and if it has, yeah, so, and it has some finite variance, then we know that this is a central limit theorem in that case. Or if our associated Markov chain is, say, reducible, a periodic positive recurrent chain, then we know that with A equals to 0 and B equals to 1, this Xn will converge to the stationary distribution. So these are some of the examples. So under this assumption, we would expect our model Un to behave exactly like this process. Well, the question is, okay, so what do we mean by exactly like? Let's say qualitatively it will behave like this. So it will have some lambda limit, but we have to figure out the centering and the scaling. That would be our assumption. And that's exactly, or that would be our conjecture. And that's exactly what happens. So before that, I just explained what assumption A means. It is ergodic. Say, for example, positive recurrent chains, this holds. Yeah, transient and null recurrent case, random walk case, central limit theorem, say, for example, holds. A big disadvantage of the assumption A is that such an assumption does not hold for a classical Pólya urn case. That is when when R is the identity, or which is same as the Blackwell and MacQueen case. So these two are this the classical case, the one that started all this, will not be covered under this assumption. And that's a serious disadvantage. So, and the reason is that these chains are not irreducible. So, yeah. So let's see the main result in this case. So the main result in this case is the following, that okay, so let us recall a bit that Zn has the conditional law of Zn is basically un by n plus 1, which is a random probability measure. So if we center Zn by a log n and scale it by b log n, then we denote the corresponding law by p subscript n and superscript cs. Then what we can show is the following, that in the case a equals to 0, b equals to 1, well, in this particular case, there is no centering and no scaling. So in this case, P is subscript n, superscript CS. So superscript CS is centering, scaling, C is centering, S is scaling, converges to the to lambda, which was our limiting law for the associated Markov chain. Okay, in case A is 0, B is regularly varying, then also the same thing holds. And in case both A and B are non-trivial and under some nice assumptions on both A and B, which are not so bad, in particular the central limit theorem satisfies these quantities, then P subscript n superscript CS will converge in probability to this quantity sigma, where sigma is lambda again. If A tilde is 0 or B tilde is 0, or it will give us the convolution of lambda with this normal random variable. So let's spend a minute or two on this theorem and try to understand why this theorem is important and what we can achieve from this theorem. First of all, note that Zn, this quantity, this is the law of, so this is, okay, so Zn, the conditional law of Zn was un by n plus 1, right? So this is, so the law of this quantity is actually, so how can I say this? Just give me a minute. So the random measure, so what does this quantity correspond to? This quantity corresponds to the random measure un by n plus 1 with the centering of a log n and the scaling of b log n. The most important thing to observe here is that the centering, which is a log n, and the scaling, which is b log n, are non-random quantities. Recall that we observed that in the urn model, there is a delay of tau n, right? Zn, the marginal law of Zn was same as the law of x subscript tau n. So tau n was the height of the random recursive tree. So if I replace this a by a tau n and b by b tau n, then this I would have expected, but this result is much more than that. It says that the centering and the scaling are non-random. That's a very important observation here. So what it says is that with this non-random, now, okay, another point. So if this holds, why is this theorem true? If this holds, suppose this holds for a tau n and b tau n, which are not very difficult to prove due to our representation theorems, due to the coupling that we have defined, then if that is true, then we know that tau n scales like log n, which we have said that the height of the tree is like log n. Therefore, what we expect is a tau n can be replaced by a log n and b tau n can be replaced by b log n. And that's why we need this nice, to push through those a log tau n being replaced by a log n, we need these nice nice assumptions, which are, well, these are good assumptions, not so bad, like this is differentiable and stuff. The other thing is that observe that all these convergences are in terms of probability convergence, but actually what we would expect is much more than this. All this un, so in this particular case, a equals to 0, b equals to 1, this pn quantity is actually un by n plus 1. What this theorem tells us, part A tells us, is un by n plus 1 converges to lambda in probability. But what we actually expect is un by n plus 1 actually converges almost surely to lambda. Right? That's exactly what we expect, and this result is known for the finite case. For the infinite color case, this is not known. So that's the point. So we know that this converges in probability. Again, we expect the same thing here, and also, I mean, in the case C, at least in the case of the random walk case where there is a central limit theorem, it was proved by Myler and Markov that this convergence is actually an almost sure convergence, and for that they needed to calculate the covariance, as I was mentioning before, the covariance and how far into the history you have to go to compute the covariance. So that's one, what do you call it? So this actually shows us that embedding that we have is not a bad embedding, and it actually gives us a lot of nice results. It actually gives us a lot of nice results, and it actually tells us that if our associated Markov chain is good, has nice properties, then those properties are inherited by our urn model. Of course, there is some delay. Our urn model is not quite as smart as our, not quite as fast as our associated Markov chain. So it is a bit slow process, but even with that delay, it inherits all the good properties. So this is for the conditional law. This is just for completion. This is for the unconditional law. And it is exactly the same. So I'm not going to go through this. So this is basically, the last one was for theorem 3 was for un by n plus 1. This is for expectation of un by n plus 1. And it is even easier to prove in this case. So we are not going to go through this. Okay. So before I go into the next part, I want to ask Ravi, do we have any time left?
We have 3 minutes left.
So maybe I can
maximum.
I can take questions maybe then. Just one thing, this part of the talk is based on my joint work with Antar, and this part is based, the rest of this part is based on my joint work with Antar and Swante. So just I want to display this slide. So just on this slide, see how the covariance is decaying. We can show that under some nice assumptions on this replacement kernel R, the covariance between any two chosen vertices. So if you choose two vertices uniformly at random, and if you assume this geometric rate of decay for this Markov kernel, then you can show that the covariance decays like rho to the power maximum of the depth of u from L of UW. I'll mention what is this, and depth of W from L of UW, where L of UW is the least common ancestor. So what does it mean? Pictorially, let me explain. This means that, see, if you want to calculate the covariance between W6 and W1, then observe that the least common ancestor is at this vertex V0, right? So all we have to see is beyond V0, this process is independent. W6 evolves independently of W1. So all you have to look is, so you, unlike what we were saying that for Zn you'll have to look all the way deep into the history, all we have to look is up to the least common ancestor, and it is not that difficult to compute the height of the least common ancestor. So the tree structure is actually a helpful thing, so it's not so bad. So maybe I'll just say that we have almost sure convergence, which we prove under this uniform geometric, uniform ergodicity, or this assumption, which is kind of quite restrictive. And we believe that these things hold, as I said, almost sure results hold. So yeah. So maybe I'll just stop here.
Thank you, Debleena. It was really nice talk, really long. We have just 1 minute to ask a very fast question if somebody has.
So let me go back to here.
Yeah.
I don't know, stop sharing. And then I can go back to this one, right?
Ok. ¿Alguien tiene pregunta, duda, comentario, algo? Rápido, 1 minuto.
Is there any interest to study, I mean, at what rate the Markov process converges to the stationary state? Meaning, you have it as an assumption, or
we have it as an assumption? Yes. In general, I think under, not even, that's a very strict assumption. That's kind of, well, that kind of assumption is always satisfied by finite state Markov chains. For infinite state Markov chains, that assumption is really an assumption, a strict assumption. It's not that there are not nice examples. There are, but they are restrictive. So I don't know if we do not assume anything. How would we estimate the covariance? I mean, I don't know the answer. If I knew the answer, I would have all the almost sure convergences.
Thank you.
You're welcome.
Okay. Thanks, Debleena, one more time, and it was really a nice talk.
Okay,
stay in touch.
You,
hopefully.
Yeah, sure.
We will plan your next talk soon.
Yeah, okay. Thank you, Ravi.
Sorry, I just want to mention Dubraska and Soraya. Que necesito hablar con ustedes dos un poco. ¿Podría?
Sí, profesor.
Desconectamos y conectamos de nuevo, ¿ok? Yeah.
Okay.
Ciao, ciao.
Okay, thanks for the talk.
Okay.
Nice talk.
Thank you.
Bye.
Thank you. So maybe next time I can visit